Common types of indexes in relational databases. In the world of database management, indexes play a pivotal role in enhancing query performance, particularly in speeding up data retrieval operations. B-tree index. At its core, a B-tree index organizes data in a hierarchical structure that resembles an inverted tree. This structure consists of a root, branches, and leaves, with the actual data records stored at the leaf nodes. Each node in the tree can hold multiple keys and pointers. The keys act as markers, while the pointers direct the search operation towards the relevant subsections of the tree. One of the defining characteristics of a B-tree index is its balanced nature. This means that all leaf nodes are at the same distance from the root, ensuring that the depth of the tree remains manageable and does not adversely affect performance, even as the volume of data grows. This balance is meticulously maintained through an algorithmic process of splitting and merging nodes as data is inserted or removed, thereby optimizing the tree's structure for efficient data retrieval. Advantages of B-tree indexes for query optimization. B-tree indexes are particularly adept at facilitating a wide range of query types, including those based on equality comparisons and range queries. For queries seeking specific values, equality comparisons, the B-tree structure enables a binary search methodology, where each node traversal narrows down the search space by half, leading to significantly reduced search times. Moreover, B-tree indexes excel in handling range queries, which seek records within a specific range of values. Thanks to the sorted nature of keys within the nodes, the index can quickly locate the starting point of the range and then sequentially traverse the leaf nodes to fetch all relevant records. This capability makes B-tree indexes an ideal choice for applications that frequently require data to be retrieved in sorted order or within certain value boundaries. Versatility across database systems. The universal applicability and effectiveness of B-tree indexes have cemented their status as the go-to indexing method across a multitude of database systems, from traditional relational databases to modern NoSQL solutions. Their adaptability to different types of data and query requirements, combined with the balance between depth and breadth, allows for consistently fast data access patterns, irrespective of the dataset size. In conclusion, the B-tree index represents a cornerstone technology in database management, providing a reliable and efficient mechanism for improving query performance. Its ability to handle various query types, coupled with its inherent structure that ensures balanced search paths, makes it an indispensable tool in the optimization of data retrieval operations. Whether dealing with large-scale data warehouses or transactional databases, the B-tree index remains a fundamental component in the quest for speedy and efficient data access. Resume. The most widely used and versatile index type. Stores data in a tree-like structure for efficient searching and sorting. Ideal for range queries and searching based on equality comparisons. Hash index. The hash index emerges as a specialized tool designed for high-speed data retrieval operations, particularly when the goal is to find exact matches. This indexing technique employs a hash function, a mathematical algorithm to transform data values into a unique address space, effectively mapping each piece of data to a specific location in memory. This direct approach to data storage and retrieval provides distinct advantages and considerations. How hash indexes work. The principle behind a hash index is straightforward yet powerful. When a data value is inserted into the database, the hash function calculates a hash value, a numerical index, based on the data value. This hash value then determines the exact storage location or bucket where the data is stored. Consequently, when a query is issued to look up this data, the same hash function is applied to the query value to quickly direct the search to the appropriate storage location, bypassing the need for a sequential scan of the dataset. The uniqueness of the hash function's output is critical to minimizing collisions as scenarios where different data values are assigned the same hash value, which can degrade performance. Sophisticated hash functions and collision resolution strategies are thus integral to the efficiency of hash indexes. Advantages of using hash indexes. The primary advantage of hash indexes is their ability to facilitate extremely fast lookups for queries that specify exact values, making them an excellent choice for equality comparisons. Since the hash function directly calculates the storage location of a data value, retrieval operations are typically performed in constant time, denoted as O(1), implying that the lookup speed is independent of the dataset size. Limitations and considerations. However, the specific mechanics of hash indexes also introduce certain limitations. Notably, they are not well suited for range queries or operations requiring sorted data. The reason lies in the nature of hash functions, which distribute data values across the address space in a manner that bears no relation to the actual order of those values. As a result, attempting to retrieve data within a specific range or in a sorted sequence would necessitate scanning through the entire dataset, negating the performance benefits of the hash index. Moreover, hash indexes may experience efficiency issues as the dataset grows and collisions become more frequent. Although collision resolution mechanisms exist, such as chaining or open addressing, they introduce additional complexity and can impact performance. Applicability of hash indexes. Despite these limitations, hash indexes find their niche in applications where rapid access to individual records is paramount and queries predominantly involve equality comparisons. They are commonly employed in caching systems, lookup tables, and scenarios where the dataset is relatively stable and operations do not demand ordering or range retrieval. In summary, hash indexes offer a streamlined, efficient solution for specific data retrieval needs. By understanding their strengths and limitations, database administrators and developers can judiciously apply hash indexes to scenarios where their advantages can be fully realized, ensuring optimal performance and responsiveness of the database systems. Resume 1. Stores data using a hash function, which maps each data value to a unique address. 2. Offers faster lookups for exact matches based on specific values. 3. May not be ideal for range queries or sorting operations. Composite Index. In the intricate landscape of database optimization, composite indexes stand out as a powerful strategy for enhancing query performance, especially in complex query scenarios. A composite index, by definition, is an index that combines multiple columns into a single index structure, creating a multidimensional search path. This sophisticated approach to indexing provides a significant boost to query efficiency, particularly when dealing with combined conditions across several columns. The mechanics of composite indexes. The essence of a composite index lies in its ability to encapsulate the relationship between two or more columns within a table into a unified index structure. When a composite index is created, it sorts the data based on the first column specified in the index, then within that sort, it sorts based on the second column, and so on. This hierarchy of sorting criteria forms a layered structure that significantly narrows down the search space for query operations. For example, consider a composite index created on the columns last name, first name for a table containing customer information. This index would first organize the data alphabetically by last name. Within each group of identical last names, the data would then be sorted alphabetically by first name. Such an arrangement allows for rapid retrieval of data when querying by both last and first names. Advantages in query optimization. One of the most compelling advantages of composite indexes is their ability to facilitate efficient searching based on conditions that span multiple columns. In scenarios where queries frequently filter or join tables based on a specific set of columns, a composite index can drastically reduce the amount of data that must be scanned, thereby speeding up the query execution time. Moreover, composite indexes are particularly beneficial for queries involving join operations with specific filtering criteria. By aligning the index structure with the columns used in join conditions, the database engine can more quickly locate the relevant rows from each table, minimizing the computational overhead associated with the join process. Strategic considerations. While the benefits of composite indexes are clear, their implementation must be approached with strategic consideration. The order of columns in a composite index is paramount. The most selective column, or the one that narrows down the result set the most, should ideally be placed first. Additionally, the utility of a composite index diminishes if the query conditions do not utilize the leading columns of the index, underscoring the importance of aligning index design with query patterns. It's also worth noting that while composite indexes can significantly improve query performance, they do come at the cost of additional storage space and overhead during data insertion, update, and deletion operations. As such, the decision to implement a composite index should be balanced against these factors, with a keen eye on the overall workload and performance objectives. In conclusion, by judiciously designing composite indexes to match the specific needs of query operations, it's possible to achieve substantial improvements in data retrieval speed and efficiency, ultimately enhancing the responsiveness and scalability of database systems. Resume 1. Combines multiple columns into a single index structure. 2. Enables efficient searching based on combined conditions across multiple columns. 3. Particularly beneficial for queries involving join operations with specific filtering criteria. Covering index. In the quest for optimal database performance, covering indexes emerge as a strategic tool specifically designed to streamline the execution of queries. A covering index is an advanced indexing technique where the index itself includes all the columns required to satisfy a query. This means that the database engine can obtain all the necessary data from the index without having to access the table's data pages. The implications for query performance and system efficiency are profound, particularly for read-intensive applications. How covering indexes work. The concept behind a covering index is straightforward yet powerful. By including all the columns needed for a query within the index itself, the database can bypass the more time-consuming step of fetching the actual records from the table. This is especially beneficial in scenarios where queries frequently access a subset of columns from a larger table. For instance, if a query selects only the columns first name and last name from a customer table, a covering index that includes just these two columns would allow the database to return the query results directly from the index. The efficiency gain stems from the reduced I/O overhead, as indexes are generally more compact and faster to scan than the complete table data. Advantages of implementing covering indexes. Covering indexes can significantly improve the performance of queries that involve only the indexed columns. The direct access to required data through the index minimizes disk I/O operations, accelerates data retrieval, and reduces the overall load on the database system. This makes covering indexes particularly valuable for high-volume, read-heavy environments where query speed is crucial. Additionally, covering indexes can contribute to more consistent performance. By relying on the streamlined structure of an index, queries may exhibit less variance in execution times, contributing to a more predictable application behavior. Considerations and trade-offs. While the benefits of covering indexes are compelling, their implementation requires careful planning and consideration. One of the primary trade-offs associated with covering indexes is the increased storage space they demand. Including multiple columns in an index, beyond what is necessary for uniqueness or basic lookups, can lead to larger index sizes, consuming more disk space and potentially impacting the performance of write operations, inserts, updates, and deletes. Moreover, the effectiveness of a covering index is closely tied to the specific queries it is designed to support. An index that perfectly covers one query may not provide any benefit for another query that accesses different columns. As such, database administrators must judiciously select which queries to optimize with covering indexes, balancing the desire for read performance against the costs of additional storage and maintenance. In conclusion, covering indexes represent a potent optimization technique within the database administrator's toolkit, offering a path to significantly enhanced query performance for specific use cases. By allowing queries to be satisfied entirely from the index, these specialized indexes reduce disk I/O, speed up data retrieval, and contribute to a more efficient database environment. However, the decision to implement covering indexes should be informed by a thorough analysis of query patterns, storage implications, and the overall impact on system workload. With strategic application, covering indexes can be a key factor in achieving high-performance, scalable database systems. Resume 1. An index that includes all the columns required to satisfy a specific query without needing to access the actual table data. 2. Can significantly improve performance for queries that only involve the indexed columns. 3. Requires careful planning and consideration as it can increase storage space significantly. Full-text index. Text-based indexes cover from documents to product descriptions and beyond. Efficiently searching through this vast textual landscape is paramount. Enter full-text indexes, a specialized index designed to cater to the expansive needs of text-based search functionalities within databases. Full-text indexes are engineered to enable comprehensive search operations over textual data, allowing users to perform complex queries that go beyond simple keyword matching. The mechanics of full-text indexing. Full-text indexing transcends traditional indexing by processing the entirety of a document's text. This process involves parsing the text into individual words or tokens and then indexing these tokens in a way that facilitates efficient retrieval. Unlike standard indexes that might only reference the location of entire records or specific fields, full-text indexes provide a granular mapping to the occurrences of each word within the textual data. This indexing strategy supports sophisticated search queries, including phrase searches, proximity searches, and conditional searches, among others. Users can query the database for specific phrases, words near each other, or the presence of certain words while excluding others. This capability makes full-text indexes an invaluable tool for applications requiring deep, context-aware search functionalities across large volumes of text. Advantages of full-text indexes. The primary advantage of employing full-text indexes lies in their ability to significantly enhance the search experience. They enable the database to quickly sift through large datasets to find relevant text-based information, a task that would be impractically slow if done by scanning each document line by line. For businesses and applications dealing with extensive textual content, such as content management systems, digital libraries, and e-commerce platforms, full-text indexing can dramatically improve accessibility and user satisfaction. Considerations and implementation. However, the implementation of full-text indexes comes with its set of considerations. These indexes often require specific configurations tailored to the nature of the text data and the search requirements of the application. For example, configuring the index to understand natural language queries, handle synonyms, or process different languages might be necessary. Additionally, full-text indexes may introduce storage implications. Given their comprehensive nature, these indexes can consume significant amounts of storage space. This impact is compounded as the volume of text data grows, necessitating careful planning and optimization to balance search performance with resource utilization. Different database systems offer varying levels of support and mechanisms for full-text indexing. Popular relational database management systems, RDBMS, like MySQL, PostgreSQL, and Microsoft SQL Server, as well as NoSQL databases such as MongoDB and Elasticsearch, provide built-in full-text search capabilities, each with its unique set of features and configurations. In conclusion, full-text indexes represent a powerful solution for navigating the complexities of text-based data search, offering precise, efficient, and flexible search capabilities that are critical in today's information-driven environment. By understanding the operational intricacies and strategic application of full-text indexing, developers and database administrators can unlock advanced search functionalities, thereby enhancing the data discovery process and elevating the overall user experience. As with any technology, the successful implementation of full-text indexes requires a thoughtful approach, balancing the demands of search performance against system resources and maintenance considerations. Resume 1. Enables efficient searching of text-based data, e.g., documents, descriptions. 2. Allows for full-text search capabilities within the database. 3. May have specific configuration requirements and storage implications depending on the database system. Unique index. Unique indexes emerge as a critical tool in this endeavor, offering a robust mechanism to enforce uniqueness constraints on data. By mandating that only one unique value exists for the indexed columns within an entire table, unique indexes play a pivotal role in maintaining the sanctity of data, particularly in scenarios where duplicate entries could lead to significant discrepancies and errors. How unique indexes work. A unique index functions by creating a data structure that the Database Management System (DBMS) can quickly reference to check for the uniqueness of a given value before allowing an insert or update operation to proceed. When a new entry is attempted on a column or set of columns with a unique index, the DBMS consults this index to ensure that the proposed value does not already exist. If the value is found within the index, the operation is rejected, thereby preventing duplication and preserving data integrity. This constraint is especially useful in various real-world applications, such as ensuring unique email addresses for user accounts, unique product IDs in inventory systems, or any scenario where the uniqueness of information is crucial. Advantages of implementing unique indexes. The primary advantage of employing unique indexes lies in their ability to prevent duplicate entries effortlessly, thus ensuring data consistency across the database. This not only aids in maintaining the reliability of the data but also supports the enforcement of business rules and data standards within the application. Moreover, while the primary purpose of a unique index is to enforce uniqueness, it also optimizes the performance of search queries that involve the indexed columns. Queries that look up data by these unique fields can leverage the index to find results more efficiently, thus improving overall query response times. Considerations and performance implications. However, the implementation of unique indexes is not without its considerations. One of the most notable impacts of unique indexes is on write performance. Since each insert or update operation on the indexed columns requires an additional check for uniqueness, this can introduce a slight overhead. The DBMS must search the unique index for existing values to validate the uniqueness constraint, which, depending on the size of the data set and the complexity of the index, may lead to increased operation times. Despite this, the benefits of unique indexes in terms of data integrity and consistency far outweigh the potential drawbacks in most scenarios. It's crucial, however, for database designers and administrators to judiciously apply unique indexes, balancing the need for data integrity with the overall performance requirements of the database system. In conclusion, unique indexes serve as a cornerstone of data integrity and database design, offering an efficient and effective means to enforce uniqueness constraints. By preventing duplicate entries and ensuring consistency, unique indexes support the foundational principles of reliable data management. Careful planning and strategic implementation of unique indexes can significantly enhance the robustness of a database, making it an indispensable tool in the arsenal of database professionals aiming to uphold the highest standards of data quality. Resume. 1. Enforces data integrity by ensuring only one unique value exists for the indexed columns within the entire table. 2. Useful for preventing duplicate entries and maintaining data consistency. 3. Can impact write performance slightly due to the additional check for uniqueness. Spatial Index. Efficiently managing and querying geospatial data has become crucial for a wide array of applications. From mapping solutions and location-based services to spatial analysis in various industries, the ability to quickly and accurately process geospatial information is key. This is where spatial indexes come into play, providing a specialized indexing strategy designed specifically for the storage, retrieval, and analysis of spatial data. Fundamentals of spatial indexing. Spatial indexes are tailored to handle data that represents objects defined in a geometric space, such as points, lines, polygons, and more complex geometries. These indexes optimize queries that involve spatial relationships and operations, such as determining proximity, how close one object is to another, containment, whether one object encompasses another, and intersection, whether and how two objects overlap. Unlike traditional indexes that are optimized for scalar data, like integers or strings, spatial indexes manage multidimensional data, taking into account the coordinates and shapes of spatial objects. They achieve this efficiency through structures like R-trees, quad-trees, or grid indexes, which partition the space into hierarchies or grids, allowing the database system to quickly narrow down search areas and reduce the number of comparisons needed to find relevant spatial data. Enhancing geospatial queries. By leveraging spatial indexes, databases can significantly improve the performance of spatial queries. For instance, when a user of a mapping application searches for restaurants within a certain distance from their current location, a spatial index can expedite this search by quickly identifying which restaurant locations fall within the specified radius. Similarly, in environmental analysis, spatial indexes can facilitate the rapid identification of areas affected by certain geographic phenomena, such as flooding or deforestation, by using containment and intersection queries. The ability to efficiently process these spatial queries not only enhances the responsiveness of applications but also enables complex spatial analyses that would be computationally intensive or infeasible with traditional indexing methods. Applications and considerations. Spatial indexes are indispensable in the realm of geographic information systems, GIS, urban planning, environmental monitoring, and any domain where geospatial data plays a central role. However, implementing spatial indexes comes with its own set of considerations, such as choosing the appropriate indexing structure based on the specific types of spatial queries and data characteristics. Additionally, the complexity of spatial data and operations means that maintaining and updating spatial indexes can introduce overhead, especially as the volume and variety of geospatial data grow. Despite these considerations, the benefits of spatial indexes for enhancing the performance and capabilities of geospatial data systems are undeniable. As location-based services and spatial analyses continue to evolve and expand, the role of spatial indexes in efficiently navigating and interpreting our world's geographic dimensions becomes ever more critical. In conclusion, spatial indexes represent a powerful tool for optimizing the querying and analysis of geospatial data, enabling applications to quickly derive insights based on spatial relationships. By understanding and effectively implementing spatial indexes, developers and data architects can unlock new possibilities in location-aware applications and spatial analytics, paving the way for innovative solutions that harness the full potential of geospatial data. Resume 1. Designed for efficient querying of geospatial data, e.g., locations, coordinates. 2. Enables searches based on proximity, containment, and other spatial relationships. 3. Often used in applications like mapping and location-based services. Bitmap Index. Efficiently querying and filtering large datasets remains a fundamental challenge nowadays. Bitmap indexes emerge as a highly effective solution for this task, especially when dealing with specific value-based queries within a single column. By employing a unique structure that leverages bit arrays, bitmap indexes offer a compact and efficient means of indexing, making them an invaluable tool in the optimization of data retrieval operations. The architecture of bitmap indexes. At its core, a bitmap index consists of a series of bits for each distinct value in the column it indexes. Each bit in the array corresponds to a row in the table. The bit is set to 1 if the row contains the value, and 0 if it does not. This binary representation allows bitmap indexes to store substantial amounts of data in a highly compressed form, reducing storage requirements and enhancing query performance. For example, consider a database table storing information about books, with a column indicating genre. A bitmap index on the genre column would create a separate bit array for each genre. Querying for all the science fiction books would then simply involve accessing the bit array for science fiction, where each bit set to 1 represents a row or book belonging to that genre. Advantages of using bitmap indexes. The primary advantage of bitmap indexes lies in their ability to perform rapid filtering operations. When a query specifies a particular value in the indexed column, the database can quickly refer to the corresponding bit array, instantly identifying all rows that match the criterion. This capability is particularly beneficial in scenarios involving large datasets and columns with a relatively small number of distinct values, such as gender, Boolean flags, or categories. Moreover, bitmap indexes can significantly accelerate queries that combine multiple conditions using logical operations and, or, not. By performing bitwise operations on the relevant bit arrays, the database can efficiently compute the result set without scanning the entire table, thereby speeding up query execution. Considerations and limitations. While bitmap indexes offer substantial benefits for specific types of queries, they are not universally applicable. One limitation is their suitability primarily for columns with a limited number of distinct values. High cardinality columns, columns with many unique values, may lead to less efficient storage and slower performance due to the proliferation of bit arrays. Furthermore, bitmap indexes may not be optimal for databases with heavy write loads. The structure of bitmap indexes can make updates, inserts, and deletes more costly in terms of performance, as changes may require significant recomputation of the bit arrays. Additionally, bitmap indexes may not be the best choice for complex queries involving multiple conditions across different columns or for queries requiring sorted results. In such cases, other indexing techniques might be more appropriate. In conclusion, bitmap indexes represent a powerful indexing strategy for optimizing queries on large data sets, particularly those involving simple, value-based filtering within a single column. By efficiently encoding data presence information within compact bit arrays, bitmap indexes enable rapid query execution, making them a key tool in data management and retrieval. However, understanding their specific advantages and limitations is crucial for database administrators and developers to leverage bitmap indexes effectively, ensuring that they are applied in scenarios where their benefits can be fully realized. Resume 1. particularly useful for filtering large data sets based on specific values within a single column. 2. Stores data efficiently using bit arrays for faster filtering operations. 3. May not be suitable for complex queries involving multiple conditions or sorting requirements. For an insightful read, kindly check out the article linked in the video description below. Don't forget to like and subscribe. Thank you.